Yay, we've made it to the last video in lesson 2. In this case, we're going to look at using a graphical technique to solve a quadratic equation. We begin by reading the entire problem statement for this problem out loud, problem 5. Complete all 5 steps of the graphical technique to solve the equation x minus 1 equals x squared plus 2x minus 7. Remember, the first question we're going to ask when we see math stuff in a statement is there an equal sign? Indeed, there's an equal sign right there. We know we're going to solve this equation. We might ask ourselves, what kind of equation is this? Right there, we see an x squared. Anybody remember how to say square in Español? You got it, cuadro. This is a quadratic. The fact that this expression on the right-hand side is a quadratic means the entire equation is going to be quadratic. Then we say we're going to solve the quadratic equation. Once again, in our problem statement, we're told that we're going to use a graphical technique to do so. We do a quick recall. To find the solutions of an algebraic equation using a graphical technique, we complete a 5-step program to salvation. Step 1 was to identify and graph the function on the left-hand side of the equal sign. Looking at the equation that we're given, we see that the left-hand side of the equal sign is the function x minus 1. We'll go ahead and say y1 is the function x minus 1. We have a choice whether or not to do all these evaluations by hand or use a calculator. This one is not too bad because the operation is a subtraction by 1. We could do this pretty quickly. Negative 4 minus 1 looks like negative 5. Negative 3 minus 1 looks like negative 4. Negative 2 minus 1 is negative 3. We notice that the y equal mx plus b form, the m, the number in front of the x, is 1, so the slope is 1 over 1. Every time I move 1 over in my x, I move 1 up in my y. In other words, the pattern is negative 5, negative 4, negative 3. We could guess that this one would be negative 2. Yep, negative 1 minus 1 is negative 2. That must be negative 1. Next one is 0. Then we have 1, 2, 3. It makes sense that the x equals 0 produces value negative 1 because the y-intercept is negative 1. When I put in x equals 0, y is negative 1. Once again, we can fill out the ordered pair format of that. I'll go ahead and fast forward so you don't have to wait. Now I have all ordered pairs on this particular table, and I can start filling out the graph. At x equal negative 4, 1, 2, 3, 4 to the left, I have the value y equals negative 5. 1, 2, 3, 4, 5. There's my first point. I know that my next point is going to be negative 3. 1, 2, 3 to the left. Negative 4 in the output. 1, 2, 3, 4 down. I also know that the slope is 1 over 1, which means if I go 1 up, I go 1 over, or the rise 1, run 1. Thus, I can fill out the entire line very, very quickly. I connect the dots with a straight edge ruler, highlight my line in blue, label this line as y1 equals x minus 1, and move on. We notice that we've just finished step 1 of the graphical technique, which was to identify and graph the function on the left-hand side of the equal sign. Let's move on to step 2. In this case, we're going to identify the function on the right-hand side of the equal sign, and we're going to graph this function on the same axis we used in step 1. Returning to our original equation that we're trying to solve, we say our first example of a quadratic function right there. In this case, the right-hand side of the equal sign is a quadratic. It's not as simple as a linear function. We're going to go ahead and set y2 equal x squared plus 2x minus 7. We could, of course, fill out this entire table using hand calculations, or we can use a calculator. Notice I haven't filled out any information here, so I'm going to go ahead and set y1 to be x minus 1, which was how I did this by hand. y2, I just hit the down button to get to y2. In this case, I'm going to hit the x and then the squared button plus 2x minus 7. I want to fill out the table. I get to the table button, which is in blue, so I hit the second. There's that little up arrow to say I'm in the second functionality. I go there. This thing starts at negative 5, but I want it to start at negative 4. So if I want to go to table set, that's written in blue, so I hit second. There's a little up arrow to say that I'm second functionality. table set. I want my table to start at -4. And I want the delta table, that little triangle, remember, is delta, from the one row to the one right below it, I want that value to have a change of 1. That's already set for me. I'm going to automatically calculate the independent variable. Let's go back to table. Lo and behold, the first x entry is -4, which I told it. Here, my y2 value, my first y2 value, is the number 1. Next, I'm followed up with -4. I see -7. At x equal -1, I've got a value of -8. Then I go to -7, -4, 1, 8, 17. I fill out the entire table of values. I'm going to write each of these as an ordered pair. I'll fast forward so you don't have to suffer through that whole process. Now I've got the entire table with ordered pairs for my y2. In this case, I got to be a little bit more careful because the behavior of a quadratic function is different than the behavior of a line. Let's start with the x value of -4. I go 1, 2, 3, 4 to the left, 1 up. There's my first point. Next one, I'm going to go -3, 1, 2, 3, and I go 4 down, 1, 2, 3, 4. Whoa, look at that. That's something interesting. Now I go -2, -7, -1, -8, 0, 7, 1, -4, 1, 2, 3, 4, 2, 1. Oh my God, it touched again. Point of intersection. 3, 8, and then we notice that the last point in my table is actually not on my graph. I'm actually not going to connect these using line segments. We're going to use curves instead. The shape of this graph is called a parabola. And remember, real parabolas have curves. Fake parabolas are called absolute values. Those are straight. So you'll see that in a future lesson. When we draw parabolas, we're going to do curves. And a parabola looks like a smiley face, kind of, if it's facing up. Once we've graphed this thing and interpolated, connected the dots using curves, we'll go ahead and highlight in red to represent that this is the right-hand side of the equal sign. We will also label this as y2 equals x squared plus 2x minus 7. We return to our description of the graphical technique. We've seen we finished step 2, which was to identify and graph the function on the right-hand side of the equal sign. Step 3, just like before, is to find the points of intersection between the two graphs. Step 1 and step 2, I create graphs. Step 3, I look, where do the graphs touch each other? Where do they intersect? If we take a look at the work that we've done on this, we see here is one point where they intersect, and here is a second point that they intersect. We'll call this one the left point of intersection, and then we'll call this one over on the right-hand side, we'll call that the right point of intersection. Remember that not only were we going to identify where the point of intersections were, but we were going to write each point of intersection as an ordered pair. That was step 4 of the graphical technique. Looks like this point of intersection happens at the x-coordinate -3 and the y-coordinate -4. In this case, we say that this is the first coordinate of our point of intersection. In the right point of intersection, we see that the x-coordinate looks like 2, and the y-coordinate looks like 1. Here, for the second point of intersection, we see this is the first coordinate. We could have also seen that these were points of intersection by looking at the table of values. In particular, the input -3 produces the output 4 in the blue function and the output 4 in the red function. In other words, this single point, -3, -4, is on both the graph of the red and the graph of the blue. It must be a point of intersection. There it is. Similarly, if we look down at the value x equal 2, the output of the function on the left-hand side of the equal sign is 1. The output of the function on the right-hand side of the equal sign is 1. And the point 2, 1 shows up on both graphs. Returning to the description of our graphical technique, we've actually done both step 3, which was to identify where the point of intersections were, and step 4, which was to write each point of intersection as an ordered pair in the form x, comma, y, and specifically identify the first coordinate of the point of intersection. The last thing that we do when we solve our equation is to set the variable from the equation equal to the value of the first coordinate of each point of intersection. Returning to our work here, we can say that a solution to this equation should be x equal to the value in the first coordinate, -3, or x equal 2. Before we box those and recognize these as a solution, we should check. Just like we did before, to check, we're going to take this value of x and put it back into the original equation. Everywhere I see an x, I'm going to put in the value -3. We're not sure if this is the case, so we'll write a question mark. Everywhere I see an x, I substitute the value -3. -3 minus 1 is indeed -4. -3 squared, that's -3 times -3, that must be 9. 2 times -3 would be -6 minus 7. -6 minus 7 is -13. And indeed, we see that 9 minus 13 is -4. For this value of x, the left-hand side of the equation is equal to the right-hand side of the equation, which says that this is a solution. Let's drop that mic and show them what we got. For the other point of intersection, we need to check that our solution actually makes a true statement in our original equation. To do so, we take the value x equal 2, put it back into the original statement. Everywhere we see an x, we substitute the value 2. 2 minus 1 is indeed 1. 2 squared is 4. 2 times 2 is 4 minus 7. We know that 4 plus 4 is 8 minus 7 is 1. We see in this situation for x equal 2, the left-hand side is for sure equal to the right-hand side, which says this is also a solution to the equation. I want to give a specific call out. Notice that the y value is -4. That's exactly what we saw in the output corresponding with the input -3. It's no coincidence that when I evaluate the left-hand side, I get -4. When I evaluate the right-hand side at -3, I get -4, and those two are equal. That's what we saw graphically over here. Same thing is true when I have x equal 2, and I evaluate the line x minus 1 at 2. The left-hand side gets value 1. That's what we saw right there. And the right-hand side also get value 1. That's what we saw right there. That must have a touching point right at that value. Here are our solutions. Last thing I'll say is when we're solving the problem graphically, please make sure to specifically identify and write down the point of intersection in ordered pair form. Identify for yourself the first coordinate in every point of intersection that exists, and then write the solutions in the form variable equal value. Check your work, box it when you do well, and then move on. Very nicely done. We have just finished lesson 2. In lesson 3, we're going to go and figure out how to solve quadratic equations using algebra. See you there.